So if I recall, last time you had an issue with the refraction coefficient K, right?
I didn't have an issue with it. I was just pointing out what the calculator stated. All right, so I'll put the thing back up in the chat.
Yeah, when you go to a refraction coefficient of what was it? Was it near 1 or something?
Very much so.
There was like a division by 0. Yeah.
No,
you know why?
What do you mean why? That's what the equation. That's how the equation works.
Do you know what a refraction coefficient of 1 means?
Yeah, it's planar. You're basically it forms a planar surface, sir. That's the whole point.
I believe that's
because because the equation adjusts. So it takes a certain radius, an initial radius, and then it factors in something, right, to adjust it, right? And the quotient works with the value, the r value minus k, or some value minus k, and then multiplies that by the radius.
Hold on. What do you mean by it's planar? What's planar? I know what a plane is.
What happens in the calculator, dude, is basically you have the radius, and then you're multiplying that radius by some fraction of sorts. That fraction is formed. If you go on the calculator site, it shows the math in it. Okay.
Right. No, well, it's very simple. Stop.
Do you want me to ask me a question?
I'm interrupting you because you already said something that's not necessarily wrong. It's just it demonstrates that you don't know what K is. K is simply the ratio between the radius of the Earth and the radius of curvature of the light rays.
Okay.
So if it's 1, it means that the light ray is curving just as fast as the Earth curves.
Right. Effectively mapping out to being planar. Creates parallel.
Mapping what out to be planar?
Do you want to look at the equation? I'll show you what I'm talking about. I'm just going by the equation.
Do you want to share screen or something? And I'll look at you.
I'll take a snapshot there. Give me a second.
Okay, sure.
Okay, Charlie, if you actually knew something, what they do is they take the radius of the ray and then model it as a straight line.
Yeah. So check this out. I'm gonna take a quick snappy snap over here. Well, I got to get the page load. Where are we now? Here we go. All right. Oh, 1 sec. Dang.
For example, 76R is 0.166 K value. Right?
Exactly. Right. That's exactly
they do.
What you need.
So they blow up the Earth to 76.
Am I supposed to be looking at an image anywhere?
Yeah.
And then do a straight ray calculation.
Yeah. So that's what Indio said.
Definitely.
Oh, I thought you were done. Go ahead.
No, I just want to know if Charlie has me muted.
Oh.
Do you hear me, Charlie?
Charlie, do you
hear me, Charlie?
Yes, I hear Indio. I don't have him muted.
Okay.
Yeah. Okay.
You have to be hammered.
Right. So what Indio was saying, Charlie, that's why in this calculator, like in the snapshot I just posted at 8 minutes past the hour, you see that they have a standard. They suggest to the user of the calculator at the bottom there, K equals refraction coefficient standard at sea level, K equals 0.17. Right. That's basically the 7/6R minus 1. So you take out the 1, you're left with 1/6, and that's about 0.6667 that they round up to 0.7. Okay. So in this calculator there, right there, where it says R prime equals R over 1 minus K, when you take that slider and you map it up all the way to 1, you're getting a 1 minus 1, you get a division by 0, it's undefined. So in the calculator interprets that as whatever, however it's handling that error, and it just basically maps.
It's an infinite radius. Yeah.
There you go. So it's just planar. That's all I was saying.
Well, yeah. I mean, my question was, what is it?
What do you mean?
When you say it's planar, you're referring to the surface of the Earth.
That was my answer to your question.
A flat Earth is being modeled as an infinite, as having infinite radius of curvature.
Exactly.
In the limited approach is flat. Sure.
There you go. That's all I'm saying. Right. So when we have what I modeled using that calculator, okay, if you scroll it back to 5 minutes past the hour, using the black swan scenario, you have Habitat or Hill House, whichever one was further, 9.41 miles.
Which image am I looking at?
Okay, the two images I put 5 minutes past the hour, both of them. It's the same quote unquote object at the same distance. Just when you take the slider and you put it at 0, it gives you an idealized line of sight shot to the to the rig
with no refraction. With no refraction on the left. Sure.
Right, and then on the right, in order to actually get it flush with the line of sight, basically lifting it up by 44.64 feet, you have to have a refraction index of almost 1. which in this calculator, they qualify that as extreme. So it's just, it's not your everyday phenomena that you would view. So what I like to pose to people is, under what conditions do we actually get this type of extreme phenomena? Like what set of humidity indexes, temperatures, et cetera, actually yield this?
Mm-hmm. Did you read the article that I posted?
Well, that's what we're going to talk about.
Sure. Okay. So how would you like to do this? It's a very short article. Do you want me to just read it out loud? How do you want to do this?
Go ahead.
Sure. So,
sorry, I just wanted to point out, like, what I'm curious about is whether or not in that article they point something out that either goes contradicts what we're breaking up here, or if they have some extra information that we're not aware of. Go ahead.
Sure. So I think the main piece that you're probably going to be interested in, I'll screenshot it and I'll post it because you probably want that. Let's see. On the left, the blue curve was entered in the refraction simulator to produce a strong refraction image. The red curve shows the refraction coefficient depending on the altitude. This curve is directly calculated from the temperature profile, blue curve, using the accepted formulas to calculate the radius of curvature of light rays from atmospheric conditions as described as deriving equations for atmospheric refraction. And that's like a link. Right image shows a vertically magnified view of the bending of the light rays under this condition. Oh wait, do I not have the simulated images? Okay, so and here are the simulated images with those conditions. Right?
It's not a simulator.
The image on the left. What?
His shit is not a simulator.
It's not a simulation?
At all, no,
would you like to explain?
It doesn't simulate anything. It doesn't simulate anything.
Okay, but would you like to expand on that idea?
So Charly, so check this out, Charly. Well, you see the ray trace you posted, right?
Mm-hmm.
Okay, so you see that those lines cross over. That would mean it's an inverted image.
Not all of them cross over. Some of them do. So it would be a small section. There would be a small section in which, it would be a small section in which the image would be inverted or more likely just blurred. But yes.
No, it would be inverted. So the rays underneath would appear on top. It would be inverted.
Right, but we're talking about like a single pixel, right? That it would have to be the case for every pixel. Yes, that's what a single ray is. I've written ray tracers myself. Oh God. Oh my God.
You can change.
Can I continue talking to Mac, please?
In his calculator, you can change the number of rays they show. Okay, so the ray is not a single pixel. But let me show you something else. So Bisman did a little trick. Not only did he tilt the camera, if you look at it, you'll see that the camera has a tilt to it, which he doesn't do in any of his other quote-unquote simulations. But he also did a trick where he blurred out, he used fog to blur out behind the oil rigs. So check this out. This is hilarious.
Okay, Mick.
Look in the chat. So why is there a tidal wave behind oil rigs? Why is there a tidal wave behind the oil rigs?
Mick, have I answered your question to your satisfaction?
Why is there a tidal wave?
You need to talk to the person who's actually addressing you. You don't get to just pick and choose who you talk to. Indio's asking you a question.
Address me, and then Indio inserted himself.
Yeah, continue with Indio.
One by one.
We'll get back on track.
I think you're wasting your time using that for this, okay? Because if you analyze this particular simulation, whatever you want to call it, for the oil rigs, it's bricked, bro.
So your issue is that he added
oil rigs. What is that?
Your issue is that he added fog to hide the waves behind the rig. Is that your issue?
That's the ocean behind the rig. It is a rig. That's the ocean.
That's your problem? Okay.
Yeah, that's my problem.
This is
I think you're missing the crux of the point, right? But that doesn't surprise me that you would deliberately try to miss the point. The point is clearly that there are atmospheric conditions that would reproduce a refractive index of close to 1 and even greater than that.
It would look like this. You'd see a big ass tidal wave behind the oil rigs.
All right, I'm not interested.
Is that what you see in the next line? Do you see like a big ass tidal wave?
I'm not interested in Indio. You're right, Indio. You're correct. You got me. BTF.
I am correct. This is old ass shit, dude. I can't even believe you're bringing this shit up. Quite honestly, this is my evidence. I can show you a bunch of shit on Bisman's calculator that's fucked up. Tons of shit. Yeah, it's trash, dude. It's real trash.
I can't hear Nick talking.
Indio, I just want to point out. By the way, I don't know if it's just me there, but your mic is very low and kind of fuzzy. I don't know if it's just me, but
sometimes I gotta reconnect it.
All right. I'll wait till it comes back there.
So is he your ringer, or are we going to continue the conversation?
Well, yeah, I just want I want to hear this. Yeah.
So is he your ringer or not?
What the hell does that even mean?
It means that he's subbing in for you in the discussion rather than me having a discussion with you.
No, we're not done there. I just wanted to chime in there, get his input there.
does the screenshot that I show you at the very least convince you that there are atmospheric conditions
No,
at
man.
which a refractive index of 1 can be created?
No, because number one,
Okay.
one thing I'm confused on in the screenshot that you posted, right? You see the graph of the refraction coefficient?
Yes.
See, on the x-axis goes from -2 all the way to 6.
Mhm.
Why is it so high? Number one, and then number two, if that's actually a thing, is
Hold
this?
on, I missed the first question. What was the first question?
Why is it go so high, up to 6, when this is supposed to be like a ratio thing, right? Anything between 0 and 1, or -1 and 1, because that's what that calculator uses.
-2 and 6. I don't understand your question.
My question is,
why can the refraction coefficient go all the way up to 6? Is that your question?
My question is, in this screenshot, the refraction coefficient does go down from -2 all the way up to 6, but in the calculator, it only lets you go from -1 to 1. So is this like a different type of thing, or like what is this supposed to represent in relation to what we're talking about?
I don't understand how the fact that the slider doesn't go up past the numbers that you'd like mean that this is somehow different.
Well, because what this is indicating to me, that what's indicating to me that these are not the same things. I know it says coefficient K, but why? Like, is this scaled up differently, or is the other thing normalized? Like, it's not exactly representative.
In the other calculator, I believe you can only set a K for the entire path of the ray. I don't think you can set. Actually, that's not true. I actually think you could set different temperatures at different altitudes. Not in that calculator. I think there's another calculator actually.
Okay. So it's not exactly representative of what we're talking about. So, and that's fine. So
it's not created from the same calculator. That's your question. I can tell you that's for sure.
Okay.
The case.
Well, there you go.
I believe that there is. What? What didn't really make sense?
You said, because you're saying now it was created from a different calculator. That part makes sense, because otherwise.
Well, yeah, no. So I think the calculator, and I believe this is true. I could be wrong about this, but I believe the calculator only allows you to set a refraction coefficient for the entire path at all altitudes.
Okay.
What do you mean meaning?
Like,
meaning that the refraction coefficient is constant with respect to altitude. But to create the black swan effect, the article claims, and I agree, that you need a refractive coefficient which is different depending on altitude.
Well, that's okay.
You can't do that in the calculator.
Okay. Well, there you go. So here we have. Well, you can set the altitude. Yeah, the height of eye. I put it as being 1 foot.
No, but you can't set a different index of refraction for different altitudes. You either have to pick one altitude and then one index of refraction.
Oh yeah, you just do one at a time, of course. But in the calculator,
that's my point.
Right. But in that scenario, you could only pick, being that you could only pick one at a time, you could still never set a refractive index higher than 1 or lower than -1. Whereas in this thing that you're pointing out here, it kind of would require something as high as 6.
Right. Do you think the limitation in the calculator means it's not physically possible? Is that where the confusion is coming from?
Well, I'm just trying to parse out how this.
My calculator for example, can't take powers of 100 to the power of 99 to the power of 99, right? Do you think that number just doesn't exist?
No, that's all I'm saying. I'm just trying to map out whether or not this is actually representative of what you can do on the calculator or not, or this is something different.
You cannot. I don't think you can do that on this calculator. But I actually do think this website has a different calculator where you can do that.
But okay, well then we can look at that. But it's just because at the moment,
right now.
if we were to use that same formula that he provides, if you plug in like this coefficient K of even 3, right? You're getting a negative value in the denominator. What the hell would that even represent on the
a refraction coefficient of 3 means
what would that mean? Like a concave like
no,
scenario?
it means that the curvature of the light ray three times the curvature of Earth. So a straight light ray would bend it into the ground very quickly.
Right, yielding some sort of concave-like phenomena, right? Like if you're at 1, check this out, right? For values less than 1.
The Earth. Yes, the Earth would look concave.
Very good. Very good. Yes. Very good. Okay, so then that means that in order to actually get the effect that we see in reality, we would need a coefficient of at least almost 1 or greater. So the question that I like to pose is, what scenario?
Only at certain points. Yep.
So what scenarios actually yield this? Like real values, not just modeling, but real combinations of temperature, humidity, et cetera, et cetera.
I mean, this table
Otherwise,
provides
it's just a model. It's just a mathematical,
right, but like to say that the model is ridiculous, you actually have to tell me what about the model is not accurate. Right? You can't just say right.
I didn't say it's ridiculous. I'm asking for some real world examples.
Listen. What about the model do you disagree with?
I'm asking for real world confirmation of what we're actually modeling.
He's asking you to verify the model with real world observations. What are you
okay, sure, excellent. So if I produce a paper where, I don't know,
not a paper, observations, experimental data.
Okay, well, I'm sorry, I trust research papers and you don't. Therefore, we're never going to have an agreement.
That has nothing to do with it. Don't strum me what I said.
It absolutely has everything to do with this.
Listen,
I can see Indio reset his microphone so we can't continue the conversation, I guess.
Charlie, is science empirical?
I don't want to do this with you, Indio. I just don't.
Yeah, science empirical.
I don't want you to like grab this conversation by the horns and like destroy it in this way. Not again. Come on.
Well, I have to translate because you don't understand what he's asking for. He's asking for, do we know that the real world meteorological conditions can even exist that would allow this to be possible? Okay. That's what he's asking.
Mick, do you accept the concept of refraction existing?
Why are you doing a red herring?
We have light bends between two different media, yeah.
Excellent. Do you agree that light bends in a continuum of different media?
That I don't know. That's what's being claimed.
Okay, excellent. So, I mean, you understand that it's just a differential case of the...
It's being labeled as refraction so as to kind of like equivocate the two. And that's what I'm not sure.
Okay, so let me ask you... Okay. So between two media, you have no issue, right? Like, you accept it.
But instead of delving into theoretics and shit, can you just say that you don't have real-world experimental data to validate the model? Or that it's just nothing that you will accept.
But I mean, I don't need it because you already said that you've done refraction between two media. Right?
He asked you for it explicitly.
Yeah, if you have
Charlie,
it, then
if you keep doing rhetorical gimmicks, I'm going to kick you the fuck out of here. So I'm about that.
Just do it already and quit your bitching. You racist.
Yeah, that's what I thought.
Just do it.
Your narrative shit don't work. Okay.
If you're not going to let me have a conversation with this guy, just fucking do it.
No, you know what he's asking for.
Waterboard me this entire time.
Look, you know what he's asking for.
Come on, no. You're going to get too frustrated and then you're going to drop another hard R here. Come on.
Charlie.
Oh, hold on. That reminds me. You're banned on site. I just remembered. Unless you want to continue, Nick, because I'll suffer for you.
I mean, if he's got the thing I'm asking for, sure. But, if there are, of course not. Well, then otherwise.
Look, that's why he deflected to what you believe and wants to talk about models, etc. Listen, I'll give him another chance. Charlie, you have one job. Experimental evidence that validates the model, right? He wants to know.
Just to start.
Do the meteorological. You win. That's easy money, man. That's not good. That's just free money, man. That's just free money. Like, what are you talking about? So,
where's my gun?
Yeah, I know. You should get a finder's fee. So it's really simple. Want the experimental evidence? Like, yes, refraction exists. That doesn't mean it exists in all possible ways. So we want to know: can the meteorological conditions exist? Right. So here's a meteorological condition we know that exists: negative 70 degrees at ground level and 150 degrees 5 inches above it. We know that doesn't exist in nature. So if there's a refractive condition would be created by that, we know that doesn't exist. So we want the meteorological condition, I don't know how I understand it, but you don't, that would cause this specifically.
I'm working up to it. You guys have to develop the patience in order to hear me.
Go for it.
Excellent. So you said that you don't know if refraction in across two different mediums you accept, but not necessarily in a continuum of mediums, right?
Right.
So why don't we first work on real experimental empirical evidence that exists? Yeah?
Sure.
Okay. So I'm sure you've already seen this.
Go ahead.
I'm sure all of you have already seen this. This is a video of a laser beam bending in sugar.
Oh, yeah.
Have you seen this before, right?
Well, here you have two distinct media, right? And as the density of the water increases with more sugar, it changes the path. That's fine.
Right. But the point is
that you can model with Snell's law and shit. That's fine.
Listen. The point is that you don't have the light beam, the laser beam, going from one line angle into another line. Here you have a continuously bending line. Do you accept that? That's what I mean when I say a continuous medium.
Very interesting. So in a single medium, it's continuously bending.
Yes. That's cool. What I wanted you to accept, right?
Very
cool. Accept that.
Let me check that out. I've never seen this before.
Okay, sure.
So and they will dub this refraction in the sense that we're all familiar with, right? Because
Yes.
in this room, it's talked about, Snell's laws, refraction, everything else is kind of like being colloquially, if you will, attributed as being refraction, but it's not because it doesn't adhere to Snell's law.
Mm-hmm. So
that's the
if you're interested in it, so Snell's law is actually an idealization of some more fundamental physics where it's only applied to the transition between two mediums.
Exactly, one instance.
Yeah, but in general, right, you could have the differential continuous case, right, which is demonstrated in the video that I showed you. And the point that I make is that
how is that model? Like, is there a equation similar to whatever the sine theta times sine theta 2, whatever, all that shit?
Yeah, so you can derive all. It's not as it's more abstract, but yes. So there are a number of different theories which have increasing accuracy, which I can talk to you about if you'd like. I actually have one of them tattooed on my ribs, literally.
Okay.
Is that the path you would like to go down, or do you accept that this is a thing?
I'm just going to check the video out there.
Sure.
I want to hold up the room there while I'm checking it out there. But
I mean, it's not a super interesting video. It's just a laser continuously bending in like a fish tank of like sugar water, right? So now I'm going to make another claim. I don't know if you're going to accept it. It might sound outrageous. That same effect exists in all fluids, including gases.
Okay.
Do you accept that, or do I also need to demonstrate that to you?
I would like to see that, of course.
Yeah,
but then again, right? So in these specific
sugar water in the air.
No.
Right. Like this is just like a tabletop experiment, right?
Right. So sugar is a dichiral molecule that changes.
Right. So what we could do.
So sugar is a dichiral molecule that changes the phase of the laser.
Very interesting.
Okay, so what we could do is try to understand. So what we could do, I will straight up tell you, I am not aware of any tabletop experiment that you can run that involves continuous diffraction with gases. I'm not aware of it.
Very good.
So if that kills the conversation for you, right?
Well, we kind of require
if that's what you need. Right? Well, no, actually, because what you could do instead, right, is try to understand what the heck is going on. Like, oh my god, the light is bending.
Yeah, right? I understand that. I understand the concept, dude. That's fine. Mm-hmm. But it all boils back to what I was asking before. Right? Once you have a model, you need to go out and experiment, and gather data, and then see if the model fits it. Period.
Yeah, that's exactly what we're doing here. That's exactly. You're not hearing me out. That's exactly what we're doing here, right? We see this.
No, but you just said hold on.
Let me connect the dots.
Hang on. Don't cut me off. You just said that you don't have the data to fit. So that's fine.
No, that's not what I said. That is not what I said. That is not what I said.
You're inferring. You don't have a tabletop example of it.
I said I don't have a tabletop example that demonstrates at a tabletop scale, right? Gas providing visible amount of refraction, at least not to the amount that you could just record and put up on YouTube, right? However, following the same requirements that you gave, right? What you could do is instead look at what you do have, form a model around it, make a prediction about the things that must happen at larger scales, and then go out and observe if those predictions match the model. And that I can.
No, but that's not my job,
absolutely.
Right? Here's the thing: is we got to this conversation after I asked you initially for the data, and we basically got here after you said like you agreed to continue with the conversation, assuming you actually had something, and then here you are providing the sugar water thing, and then finally saying, "Oh, well, I don't have anything else."
No, I'm working on steps. I'm doing steps, right? Because you said you didn't believe that refraction in a continuum existed, so then I stopped.
I didn't say that. I said I'd never seen it. I'd never seen it.
Okay, well, right. Well, I think that's a prerequisite for you to believe it, but okay.
Well, I understand this now. Yeah, I see it happening in sugar water. That's fine. So now let's take that to the real world in the sort of context that we have at hand. And does this actually map to that? Yes or no?
So do you think that observing it in sugar water opens the door to maybe there is something that would explain it to all fluids?
And it might. I don't know, but you supposedly have.
Excellent. Let's find out.
Okay, so go ahead and bring that forth, please. That would be great.
So our better theories of physics in the field of electromagnetics are Maxwell's equations, right? Which predict things like Snell's law. You can actually get more sophisticated refraction behaviors from just studying those laws, based on those laws, right? You have this number called the refractive index, which you can measure from different materials, based on certain experiments, right? The refractive index of the composition of air is very close to 1, but not quite 1. And so in order to measure any significant deviation from a straight line, you sort of have to do it over long enough distances, right? But you could do this with any material in theory. And so we develop a table of like the index of refraction of all sorts of materials, like glass, water.
I've seen that in high school, dude.
Yeah. Okay. So you've seen it. Excellent. Right.
Yeah,
so
dude.
using those numbers, right? Using that data, you can also develop relationships between what that number is for that material under different conditions like temperature, pressure, density, yada yada yada. And so you build up this huge empirically defined table, right, of values of index of refractions for different materials at different conditions.
Okay. Do we have that?
Yes.
Okay. And how is it modeled and how is it verified?
What do you mean? How is it modeled? It's empirically measured. It's a value that's empirically measured.
No, I understand that, but then you build a model off of that, supposedly. Just sort of like
no, you don't. You're not hearing me. The model.
You have the data.
The model is already had, right? Like the data just tell you the values of what the parameters are that fit into the model. In this case, the index of refraction of both materials, right? That's just empirically determined.
Yeah, but then what do you do with those values? Right, because in Snell's law, you have index of refraction 1, index of refraction, you use some multiplication against angles and shit. But that formula, that's basically a model. That's what I'm talking about.
Right. You asked me, under what conditions can you get an index of refraction that's close to 1, for example? That's one of the questions you asked me, right? Well, no. We can pick any... No? Am I misremembering, or did I mishear?
Oh, excuse me. I thought you were talking about for a material. Yeah, excuse me. In the context of what we're talking about, with the Black Swan thing, yeah, that's right.
No. You asked me, what conditions could possibly happen such that we have an index of refraction, or coefficient of refraction close
meteorological conditions.
Yeah.
Well, hold on, you're jumping 3 steps. Please, just hear me out.
No.
One of the things that you could do. I'm working towards it. Jesus. One of the things that you could do.
I don't need you to lecture me or the room on how.
Apparently, I do.
I don't.
No, you don't, because you didn't have it wrong, dude.
Notice we're getting closer and closer there. Baby steps. Is why I think you do.
Dude, the only thing you said correct is that air. We know the refractive index of air empirically. Everything else is bullshit. Bullshit.
Yeah, because Charlie, you're tying in things and you're walking through. You're creating like this massive narrative, and then supposedly we're all kind of anticipating that you got the fucking goods at the end of the line. Yes. You haven't even shown that you have the goods initially, and then explain how it got there.
God, so you're afraid of following the train of thought. Is that where we're stopping?
No,
is that why we're stopping
No,
here?
I'm not.
Okay, then follow me. I'm not stopping. I'm continuing to talk. The question now is, so first of all, are there any 2 combination of materials or any continuum of a material that would produce a refractive coefficient close to 1? And if that is the case, are there any meteorological conditions which can produce that combination of indices of refraction? Like those are the steps that the 2 high-level steps that I still have, by the way, within those 2, several others. And if you're going to interrupt me every single time I go through one, we're never going to end this conversation. So
why don't you just produce the meteorological conditions that caused it?
Oh, God.
Why don't you just produce that?
Don't interrupt him.
What's so hard about that? Just produce it.
Yeah, Charlie.
So hold on.
Charlie, Charlie, check this out.
Everybody sees you fucking shucking and jiving, dude.
We're not asking you for hypotheticals that may lead one to that it's possible that this exists. We're asking you for it to actually exist. Okay, then drop the data.
This is how it works, because you keep saying it doesn't apply. Listen to me.
Look, here's how you start. You drop the data table, showing that it's true, that it's possible, whatever, in the chat, and we talk about it.
Showing that what's true.
Period. The question that we asked.
What was the question you asked?
You're kidding me.
Whether or not there are meteorological conditions, whether that can cause that.
In that environment,
the issue here is that I'm trying to illustrate you a process.
I don't need an illustration. I don't need a process.
You do.
I do not need no, don't tell me what I need.
You don't understand it.
The data. I don't need the data, dude. I need the data. Excuse me. I don't need the process. Drop the data table in the chat, cite it, and then afterwards explain how they got that, and then we can check it out. That's all, man. We don't need fucking storytelling. It's not bedtime story time. God damn it.
I you asked me for an explanation. I'm trying to give it to you, but you're unwilling.
No, we didn't. You asked your question.
You're absolutely unwilling to give it, right?
I didn't ask you for an explanation initially,
ask the question, dude. You know what he asked for. Stop playing around, man. You know what he asked for. You can't produce it.
Yeah. This is exactly why I wanted to bring this back up, because the other day it almost seemed like this entire thing that we're observing now was at least was avoided, whether it was intentional or not. But now it's coming to fruition, and I had to see it to the end. It's exactly what I expected.
Do you disagree do you disagree that there are specific combinations of air temperature that can produce an index of refraction of 1?
I don't.
That's what I'm trying to demonstrate to you, but you keep la-la-lying out of it. Shut the fuck
Get the
up for
data
5 minutes, and I will tell
Don't
it to
me
you.
that. Get the data table
Yes.
that demonstrates that these were actually real world examples, and then we can talk.
No.
Okay?
That's not what
Don't talk
that's
to me
not
like
what you're
that, dude.
asking for. You're asking
Yes,
for
I
A.
am.
He's
When I'm trying to give you
telling
A,
you what
you change it to
dude.
fucking B.
No, dude, I asked for.
If you don't accept that there are combinations of air or specific atmospheric conditions for air
Then you
that can cause that index of refraction, then why the fuck would I show you a table that demonstrates those values at all? Because you're not going to believe them.
You missed the second part of the question then, because you can create like a theoretical matrix of all sorts of different values that was.
It's not theoretical. It's empirical.
And then the second part of the question was, can these actually exist at the time, where the black swan was taken? Kind of like what Indio said before, right? If you have, two pockets of air that are like,
what? That's an extra condition that you were adding now.
100
What?
degrees or like 100 degrees in, difference. That would create the effect, but that can't actually exist, right? So it's not enough just to have the theoretical.
So if I don't have the measurements on that day, right, you're just going to say, oh well, you haven't explained anything.
No, man, if you know where to get them, then by all means, man, like go ahead and come back.
If I know where to get them, the measurements for that day on that spot. That's a fucking ridiculous request. That's crazy. All that I should have to demonstrate to you that it's possible is demonstrate to you that it's possible for air to be at a certain temperature at a certain height, and that's fucking it. That's fucking it.
Well, hang on. You haven't even shown that this constant curve thing is even possible in gases. You admitted to yourself that you don't know where to look, to produce, to find
because you
an example.
artistically complain that you don't want steps of it explained to you. Yes.
I don't need the explanation. I don't want the explanation, dude.
Because you're not intellectually curious. Don't you think you need the explanation to understand some of the fucking points that I'm making? You're using the absence of knowledge from your mind as an explanation as to why it must not be true. But you don't fucking listen.
He's not.
How do you know that you're wrong? You're listening to the thing that's
You're a liar, dude.
No, dude, you're strawmanning the entire fucking
Charlie,
dude.
I'm just muting it. Charlie, stop lying. He's using your absence of evidence as a reason not to believe it. He understands the explanation. He understands refraction. He understands it perfectly fine. Now, you don't have the black swan. Okay, fine. Do you have any data at all from anywhere that shows that this is possible? From anywhere?
Yes, absolutely.
Okay, show it.
I have the data right here. That I have a table of index of refraction of air based on temperature, for example.
Measured.
What?
The measured meteorological conditions of the day. Yeah.
I don't have the measured meteorological conditions of that day on that spot. Like, that's an insane request.
From anywhere.
From anywhere.
Yeah,
I mean, why does it need to be anywhere? Why not in a lab? They got air, they heat it up to a temperature, they measure the index of refraction. What's so hard about that?
Okay, because we're testing the natural world. We need to know that the conditions can actually exist in the natural world.
Why would the world behave differently?
Why are you interrupting me?
If you're outside versus in a controlled condition.
Does it rain? Does it rain in a lab?
You can simulate rain.
Oh, Jesus Christ. No, you can't. Water falling down
You absolutely can. Rain. What do you think?
Water falling down is not simulated rain, dude.
Oh my God.
Rain is water nucleated down in fucking dust particles.
Sure.
Okay? That's not fucking water falling down. You don't know what you're talking about, again, as usual.
Buddy.
But listen, we want to know, in the natural world, this model, does it actually model reality? But we need to know what reality is, right? To see if the model checks out.
Sure.
Why do you have a problem with that?
Do you think that being in a lab suddenly means that the laws of physics don't apply?
No, but that doesn't mean the conditions outside the lab exist inside the lab, right?
Interesting.
So we don't, no one cares about your interesting. Look, you're the dumbest fuck in this chat, and I don't know why you're the condescending one. That's the crazy.
No, well, nobody told the people pay me the big bucks, dude.
Yeah, well, they must be fucking morons if anybody's paying you money to do anything.
I guess so. My bank account's pretty happy.
Yeah, triangulate a satellite. Try that again.
Trilaterate, you fucking moron.
That's not what you said. You said triangulate. Yeah, that's right, dude. You're a dumbass.
No, I said trilaterate. Earlier today, as an example of a simpler case to the young lady here, I said triangulate. But no, you've heard me many times have this discussion where I clearly explain the process of trilateration, right? Intersecting spheres.
Yeah, I've heard you say all sorts of shit. But basically, throw shit against the wall.
I've heard you say way worse, and I think you know exactly what it is that I'm talking about.
Yeah, Charlie, you're on borrowed time. Okay, so...
I thought it was talking with Mick. I thought it was talking with Mick.
That's what I've been trying to do this entire time, to be honest.
Yeah, you're a snitch. So you're a snitch, bro, right?
What?
Yeah, that's right, bitch. You're a snitch.
How are you not apologetic about yelling the hard R at a black man that you had in here?
Yeah, I actually didn't yell the hard R. I got a Boston accent.
Oh, really? Should I pull up the clip?
Yeah, I actually just listened to it today. It comes out that way.
Well, I bet you hear it
tons of time.
It just
Fuck the
comes
kind
out
of hobby
that way.
guy, right?
does it really matter if the guy heard it the way everybody else fucking heard it?
I don't
Who
care.
cares?
Well, you know what happened to me? I got like 12-hour fucking demoted. So fucking what, snitch? That's
Do you
right,
think I
snitch.
care?
Anyway, let's move on. Yeah, of course you don't. 'Cause you have no honor. You're a coward. Anyway, let's move on. Do the meteorological
fuck?
conditions that make ass war. Do the
Why the
meteorological
fuck
conditions.
would I treat you with any sort of fucking honor?
No, you have no honor. You just don't have honor. You're a piece of shit. Anyway, we're moving on to. Do the meteorological
Yeah,
conditions.
because yelling
This
Hokar
is
or some
nature.
innocent black man is totally the honorful thing to do, right?
So what?
Dude, don't tell. Listen.
Hey, if that is the hard R, as you
Yeah.
claim it is, you just broke TOS posting that shit, you dumbass.
Yeah, why are you obsessed with this? Talk about the information or don't talk.
I'm glad you asked. So
No, that was a
no,
rhetorical
no.
question. That was a rhetorical question.
You step into that.
Dude,
Look, I'm
never
glad
do
you
that
asked.
again.
Nobody pull up. Yeah, nobody pull up my book.
This sounds fun. What's going on here?
You guys talking about butter?
Butter?
Guns
I
and
heard if you put enough butter along the world, you could slide straight off the edge and off into space.
What?
Yup, if you just nay on that beat hard enough, you will fly off onto Neptune.
The comic relief has entered. The comic relief has entered.
I needed that.
Like Mick, it's up to you. I don't think we're ever going to get the empirical evidence out of Charlie to support his
No,
claims,
it's done, man. It's done, right? This entire exercise, I thought, was to, or initially it was going to just be to investigate the article. Right? I was curious if whether or not it mentioned anything that contradicted the calculator or explained it away or whatnot. I kind of got that, right? Because even Charlie mentioned, like in the graphs produced, right in the article, you have indexes of refraction higher than 1. Okay, you can't really do that in the calculator, so it's kind of indicative that the calculator is incomplete overall. But even with the
if you notice, well, I was just going to say, like, they are two. Like, there's the ray tracer, and then there's the other calculator, right? The other calculator, if you look in the graphic, right, you'll see where it says effective radius.
Yeah.
So all it does is it takes the K coefficient, expands the ray to like whatever the effective radius would be, and then does a straight ray model. The ray tracer just it literally takes a pixel and runs it through like it does like a vector transformation. So it runs it through and changes its direction as it goes through this distance, and like it has like steps, right? So like if you look at it, you'll see like how many steps you want to use, right? So it'll move a certain number of steps, and then it'll either move up or down on the screen. So So say the pixel started in the center, right? And then like the ray trace says, oh, you're supposed to move down after some distance, right? Move you 1 meter, move down, move you 1 meter, move down a little more, move you 1 meter. It just shifts the image. It's just it doesn't simulate anything. It's just
Did you see my screenshots of what this entire thing came about from?
Yeah, further up. There's all sorts of problems with this calculator. Yeah, sure. I didn't get a good look at them.
Right. Basically, in the left hand, that's the idealized what should actually happen on our globe of said dimensions and shit with no refraction. The black swan should be cut off basically halfway. In order to actually get to a view of what we actually see, that's the index of refraction that's required. That's why I was probing Charlie on that, because that's extremely high index. 1 basically means it's planar, right? It lifts the entire thing, so you have an infinite radius. And then when it's higher than that, according to what Charlie was talking about and what the article points out, anything higher than that creates actually like a concave, like an inverted radius, so to speak. So,
well, I think it's a perfectly fair question to say, hey, do these conditions actually exist in nature? How is that a not fair question?
Yeah, I've been asking a lot of people that. I mean, most people just goes over their head there. But when you said there's an article,
I just ask them because you're saying everything is refracted up all the time. Like, how do you know that that's the general condition, right? That every time we go to the beach, everything's being picked up over the curve. Like, every time, how is that the general condition of the air, right? And then that would mean that like the rare condition would be ships over the curve, right? That would be the rare condition because that's when it's not refracted and that's when you see the geometric fucking horizon, right? So like, everything's like on its head.
Yeah, it can go either way. That's why this particular argument is kind of interesting because right from the get-go, when they started observing stuff and say, oh, it must be a ball, how do we know that they were just not looking at it in a condition that, like what you're saying, that was like the rare condition, but then they formulated all their stuff based on that, and from there you get your radius and and whatnot, supposedly. So yeah, it's I find it interesting. So I like to use it because, you know, there's maths and numbers and shit.
Well, I just noticed that like they like this refraction thing's again tossed back and forth. So like we've always go, okay, what's your evidence that something we picked up around the curve? And then they'll show like there's the clay in the butane tank, and then there's like the dry ice, and then there's like they have to. What I noticed is they have to make an extreme condition with some substance that has a refractive index that's like 30% higher than air to even demonstrate it, that it's even possible, right?
Did you see the
refractive index of 1.4, and CO2 it has a refractive index of like 1.3, and when they're using it, it's super cold, right? So it's like this isn't a natural condition.
Another one that's really interesting. Another one that's really interesting that came about not long ago. I think it was Mez who posted it. You ever see that one where the guy takes out a laser, he points at a white wall, and he takes out a hot iron and approaches the laser's path and deflects? That's another one. But that's like what, a difference of 300, 400 degrees Celsius or something? Whatever.
Like 1 inch. In like 1 inch, man. Like, you know what I mean?
Yeah. I mean, it's very interesting because one could suppose that of differentials lower than that over longer periods, the minute shift could, compound and then yield something. But then you're still faced with the empirical evidence, which they don't have. So there's a bit of an impasse in the entire thing still.
It's funny that talking to left. He doesn't even want to listen to what he didn't understand.
Oh, Charlie left like 10 minutes ago. I know.
That's what I mean. Hilarious.
Oh, did he just leave voluntarily? Is that what happened?
Oh, Charlie, I heard you on Ladies Night with Charlie, and I heard you say that you've heard him before. Yeah, he's a disingenuous schmuck, dude. Totally.
Yeah, I mean, you totally exposed him. He really didn't want to talk to you, Indio. He was like, "Can I talk to Mick, please? I don't want to talk to this Indio guy."
Oh yeah, I've smacked around a few times, dude.
That was pretty comical.
You stole my smack.
Lights away, right? And like he cited some guy, and then I went and found the guy, and I got a video of him saying that light's a particle, and he freaking spazzed out. It was pretty funny. So I used his own citation to prove him wrong, and obviously he's a condescending fuck when you do something like that. Like he freaking went nuclear.
That's
why he exposed himself. He exposed himself.
Yeah, that's why I wanted to investigate the article, because I was sure there was going to be something in there that was going to be juicy, and I think we found it. Seemingly contradictory stuff, or just more theoretics that have yet to be mapped onto reality and demonstrated to actually be valid. So I kept probing him for a model. He's like, "Oh, you're an idiot. I got the indexes. That's all we need." It's like, no. How do you plug those in? Like Snell's law. Yeah, you have your indexes, and then you plug them into some, multiplying by, sine theta and shit like that, dividing by other stuff. Great. Now, what do you do with these ones that you provided? What happens? He couldn't do it. He couldn't answer. So that was fun.
Yeah, it always was on the same thing. Okay, is science empirical? Like that's what I was trying to get out of them, so that they'll say yes. Because if it's not empirical, then what are you talking? Then you're violating the entire philosophy of science, or the whole foundation of science is empiricism. So if you just go into explanations and models and theories, that's not science. That's just storytelling. And so you got to have the data to back it up. And like if you're going to say, my model predicts this, okay. And he said, yeah, we can do this. And he kept, and this is what Charlie does, right? He always says, yes, I have the information. I just can't show you because he wouldn't believe it. All the time. And he's never shown anything.
He seemed to have almost tried to get away with another one of those when we were asking for him, like, do you have the data? And he said, yes. And he was about to produce a table of different indices of refraction for different, things. That's fine. And those presumably were determined empirically, like in a lab setting. Fine, but that's one little bit. We're asking for the full context, data on the output of some sort of test, in the larger context, using these things that are supposedly empirical. Knowing
index of refraction is fine, right? You can test so what they tested was temperature, humidity, pressure, CO2 content, and there might be one other thing. And they tested at a bunch of wavelengths. So it's been tested up to not all the way to infrared, like maybe 790 nanometers or something. But they tested at each of these, right? So there's two different formulas that they have. But that's fine. But that doesn't tell us how the light propagates through air. That always tells us what, the refractive index of air is a certain temperature, pressure, humidity, right? That's all that tells us. It doesn't tell us how the light's going to travel through air. Doesn't tell us how that air is distributed through the Earth, right? Doesn't tell us any of that.
Exactly. Yeah. Like at one instance where you have air that's like super cool or standard, and then another little pocket right next to it of said temperature and whatnot. Yeah, you can expect that to behave in a way that you're maybe getting in this setting. But how does that extend to the larger context? Because they don't have the data on, what the conditions were. They can only guess that, it must have been like what we see in the lab because of all these other things that they basically assume. Yeah.
Yeah. I agree. I mean, their model assumes like a spherically symmetric atmosphere, right? That extends out radially, right from the center. That's their model. Spherically symmetric atmosphere that's radial. Like, there's no evidence that exists in nature at all. So what are they modeling exactly? They model something that don't exist. They model an ideal system that doesn't exist.
Wait, can you repeat that last one? What is it? What was it? Symmetric?
Spherically symmetric atmosphere. So there's a vertical gradient, right?
Right.
Okay. Radius, right? So the atmosphere is spherical. It's a spherical atmosphere. It's atmosphere, right? So it's a curved atmosphere, right? So let's say we had a Snell's law gradient, right? So let's say it's 1 degree Celsius for the first 1 foot and 2 degrees Celsius at 2 feet, so on and so forth. That layer is going to be curved itself.
Yeah.
So think about that.
Yeah, I got that. But in that sort of setup, these are discrete.
The light ray can't go straight. It can't. It's literally impossible. If your model is like that, even Andrew Thomas Young says this. A ray in a spherically symmetrical gradient atmosphere can't go straight, no matter what, because the atmosphere is curving.
Wait, even if the light is passing through at the same altitude, whereby it's kind of sandwiched in between two different layers.
Well, because if it goes straight, then it'll be at a higher altitude.
Oh, eventually, yeah.
The atmosphere is turning down, right? So,
right, it's true.
So the laser ends up going into space, right? So right. It has to curve.
So was it like light would bend towards
the lower density?
Towards the lower density, okay.
Yes.
But in what direction, up or down? Like if you have two parallel, let's say you have two walls of gas, sandwiched in between glass or something like that, and you pass light into it from one side, from the higher density to the lower density, it'll bend towards like what the normal, or does it go down or up?
It should bend. Well, what actually happens, without getting super technical. So, I'm sure you've seen diagrams of waves where they extend out like circles, right? So what happens is when there's a gradient, that wavefront ends up twisting. So the direction of the light changes, right? So the phase front gets tilted. So let's say it's going horizontal for a section. The lower part of the wave will be in the denser part of the medium. And like say you had just for Haas, say the wavefront was a foot long, and the top part of the foot is in a lower density, and the bottom part is in a higher density. That end will end up twisting it, right? Because the bottom part will end up going slower than the upper parts. So that turns it. You understand what I'm saying? So it'll turn it down. The wavefront, yeah. So it'll twist it down. It's like trying to catch up to something. Like, say you had a ruler and you're making it go through water, and the water was thicker at the bottom than the top. But it always goes only one speed. So the top part of the ruler would go faster than the lower part because the liquid on top is less viscous. So it would end up turning the ruler. You get more drag on the bottom than the top.
So what would that create? Like instead of just a ruler that just inflects at the surface, creating like a bent ruler, it would create like a U shape.
It ends up rotating. It ends up rotating it, right? It's because the bottom part can't keep up with the top part.
What the fuck? Okay.
Yeah, so that's basically what's happening because the denser air at the bottom, right? So the bottom part of the wavefront goes slower than the top part of the wavefront, so that wavefront ends up turning. And because it's turning, and it always goes normal to the perpendicular to the wavefront, right? So as it turns, right now the direction the light ray's heading would be down, right? So over in a gradient medium, it'll turn, like it'll make a curved path. That's the idea, at least.
Okay.
But in a spherically symmetric atmosphere, then it'll always turn, right?
Hey, Charlie's back, by the way, I just noticed.
Yeah, I was kicked for pointing out somebody here likes the N-word.
You were kicked.
It's not the topic. Don't bring it up again or else you're getting kicked forever.
Yeah, I know, it's defamation.
We're moving on. Yeah, don't bring it up. Shut the fuck
Sure,
up.
would you like to continue our conversation?
Yeah, the
I'm
actual
happy to.
conversation, which isn't about that. The one that's about the room topic. That
Yeah,
one.
we were talking about refraction, right? Right. Mick was like,
well, kind of.
demonstrate to me that that the proper conditions have been measured that can generate a refraction coefficient of close to 1. Right. That was the question.
Right, in the black swan scenario. Yeah.
No. He added that afterwards. Let's work towards it, right? Let's first accept that it's possible, and then we can see if it applies in the black swan scenario.
Yeah, accept the claim I'm trying to prove, and then we'll move on. Fuck you.
Yes, as I said, baby steps, right?
It was a
It's
two-part.
apparently
Accept the
necessary.
claim you need evidence for, and then we'll move on. I don't think so. Get the evidence.
What? Accept the claim you need evidence for?
Yeah, prove it's possible.
I'm working towards that.
Now,
I don't know
in theory,
if you know what a
nature.
reconstruction is. Yes, sure, whatever.
In nature.
So, Mick,
In nature. Repeat back to me what I just said.
do you accept this as the formula for
Repeat back to me what I just said. Repeat back to me what I just said.
for a medium?
Yeah,
Or if you
I don't care about your
then let's
muscle.
go into that.
Bro,
Wow, Indio, you really love inserting yourself.
repeat to me what I just said.
Mick, are you there?
Is this equation in Charlie? Is this equation in nature?
Mick, are you there?
Yes or no? Is this equation in nature?
Nature's not math. Mick, are you there?
Okay, cool. So we want the in nature.
Excellent. Do you accept that this equation accurately models?
No, I do not. We need the evidence.
Are you Mick? Are you Mick?
Doesn't matter.
I mean, if you don't accept it, we can go into it. If you do accept it, then I can move into my next point.
In the panel, then just don't talk.
Charlie, should he accept it without
I'm happy to
evidence to
talk to
verify
everybody in the panel,
equation?
but this guy just like fucking jumps at the chance to interrupt you.
Charlie, shouldn't you accept that if there's no evidence to support the equation is accurate?
Okay, if he doesn't think that the equation is accurate, then I'm
Why
happy
can
to
you
present
never
the evidence
answer
that demonstrates that well, it's difficult for you to comprehend that the question is being answered if you interrupt me halfway through it.
It was a yes or no question.
Or
You didn't
actually,
say yes
honestly,
or
I
no.
don't even know that would make a difference for you, but
You didn't say yes or no.
I would have asked.
do you accept the equation, or do you not know the equation, or can we talk about it?
Why are you asking if he accepts it when you haven't presented the evidence, dude? Why are you doing that?
I think he's a big boy and he can answer for himself.
Yeah, you try.
I mean, I'm gonna ask something similar, dude. I don't know enough to accept this outright. I've never seen it before. Where did it come from?
Excellent. This comes from a 1936 paper on the study of refraction of air under different atmospheric conditions. And if you don't believe me, I can paste the paper and we can go through it.
That would be interesting.
Excellent. So here is the initial reference where I found it. The P is pressure, the T is temperature, and the delta T over delta Z is just the change of temperature over per unit change of elevation.
Hold on. Here we go. Okay.
But let me go to the actual paper, 1936.
1936, bro. Not even close.
87, dude.
I read this paper like, I don't know, 6 years ago.
It's 1936.
Reciprocal even angle paper is 1936. That's the link we posted. Monitoring the refraction coefficient in the lower atmosphere using a controlled setup of simultaneous vertical angle measurements.
Hold on.
Yeah, dude, this was first published in 2010, bro.
No, it's not.
That's
yes,
what it says at the top.
This paper cites the equation, right? The paper, excuse me, not 1936,
okay.
1939.
39.
Right, but since you don't believe the equation that they're citing, I guess we have to go back to that, right? See, this is what you're doing. You're like asking, you're introducing an infinite recursion of doubt. That's fine. Let's do that. Let's do it.
It's not infinite. It's not infinite, dude. Things have a start at some point.
So let's go to so that's the sequence from 1 to infinity, right? Brock's 1939.
Yeah.
Oh, it's in German. Let's see if we can get a nice translation.
Shit.
Every paper you look up, sorry, I've already read it. Even the German one.
That's great. You got a big brain, buddy.
He just
you're trying to play catch up, dude. You're just a pretender clown.
Yeah, he just figured out it's in German. Has to translate. He didn't know that before.
Correct. No, you're correct. I tend to believe physics papers that have been published and
just reading them now
for over almost 100 years.
Yeah,
correct.
You haven't read it.
Yeah, so you take them on faith at face value initially.
No, it's not faith. It's not faith.
Yeah, you just said it, dude. I tend to believe.
No, it's not faith.
You just said it.
Listen, if you want it, I don't want to get into an epistemological, philosophical discussion right now, but I can. Do you want to have that conversation? Or would you like to have the conversation about the physics?
Hold on, Mick. Charlie, but Charlie, you didn't read these papers, so you're not basing it upon the peer-reviewed research. You didn't read these.
I have enough confidence that the paper's correct.
What did you read the abstract or the conclusion? Which did you read? Did you look at the data? What part of the?
What does it matter?
What did you read? Well, how do you know what it says? How do you know what to believe? Charlie, I'm asking, how do you know what to believe in if you don't know what it says?
Okay. So it sounds like you want to get.
It must agree with my delusion.
It sounds like you do want to have a conversation about the epistemology, which I guess we're going down that route. Then why are you asking me the fucking question, you fucking moron? All right. The reason I believe peer-reviewed papers. All right. The reason I believe peer-reviewed papers is because from when I was a little kid in science class, right, I would read claims in textbooks that my teachers would tell me, and I would go, "That can't be true. That's bullshit." So then I would look into it myself.
Great.
I would do my own research on that subject, and then I would find out, holy shit, they're actually correct. Then times later, a similar thing would happen. Teacher would say something, I'd be like, okay, that sounds about right. I would read something in the textbook, and I would be like, that sounds about right. That seems plausible. Then I would read something else that I would think, that cannot be true. That really can't be true. And then I would go and verify it, and then I would do my own research, and I would see, holy shit, it works out. All right, so in order for me to not be catatonic, all right?
Okay, that's enough, Charlie. Enough. What I asked you was, you said, I tend to believe peer-reviewed papers. Well, you didn't read these peer-reviewed papers. So how are you tending to believe them when you don't know what they say? Every word could contradict what you believe is true.
Now you're going
to address what I'm saying?
Do you not accept that the very first paper that I pasted agrees with the interpretation of that equation and that paper is peer-reviewed?
No, it does not.
It does not. You think the paper disagrees with me?
Did you read the paper?
Yes. Yeah, the first one that I pasted, absolutely, yes. You think that paper disagrees?
You didn't even know what the title was. You told us from the 1930s.
No, you fucking moron. I'm talking about the initial paper that I pasted.
I'm going to go from memory. I'll just go from memory, okay?
Oh, Jesus Christ. Why would you ask me about the epistemology if you're not interested in it? That's so fucking dumb.
No.
Anyway, if you don't accept
epistemology, but you.
Yes, you did. You asked me what it is that I believe the paper.
You've never read the paper, and you know it.
And I'm giving you the conclusion. So, by the transitive property.
The conclusion.
I know the transitive property is difficult for you guys to understand, but by the transitive property, if peer-reviewed long-standing paper A asserts claim made by paper B, and if I believe paper A, then I must also believe paper B.
Believes it.
No, it is in paper B.
Please. Yeah, I know you guys also struggle with language and definitions, right? So,
but you don't know what it says in paper A or B. What agrees with what?
So hold on. Do you at the very least agree that the initial paper that I cited takes that equation to mean what I say it means? Meaning it is the equation that will tell you the refractive coefficient for an atmosphere at a particular pressure, temperature, and change in temperature over elevation.
No, what it tells you is if you have a spherically symmetric gradient, right? How the right way will deflect based upon pressure, temperature. That's what it tells you. Doesn't say anything about the Earth and its meteorological conditions at all.
Correct. I never said anything about the Earth with respect to this.
And why are we care? Why
you just agree with me? Okay, excellent. So you agree with me that this equation gives you the refractive coefficient for the atmosphere, giving a pressure, a temperature, and a rate of change of temperature with a Z value. Right? I mean, that's what you just said. Nothing said necessarily about the shape of the Earth.
It compares the radius of a ray to the radius claimed to be of Earth. That's the coefficient, right?
It can be seen as that.
The radius of the ray.
Can you point to me in the equation here where the R is?
God.
503 p over t squared, parentheses, 0.0343 plus delta t over delta z, parentheses close. I don't see anything about an R. I'm aware that there is another equation that equates this to the radius curvature of the ray and the radius of the Earth. I'm aware of that. But because what is at contention here is the shape of the Earth, let's dispose of that for a second. All right? Because that's unreasonable to you, Indio.
So what's the formula for? You said it was for the K value. What's it for?
Yes, it's for the K value. In the first paper, it's
is X the K value the reciprocal of the radius of the Earth? Yes or no?
It can also be equated to that. Yes.
Okay, that's what it's used for, right? When you get the value, that value will give you the radius of the ray.
What are bananas for, Indio?
Yeah, so you're contradicting yourself now.
What are bananas for? It's not a contradiction at all. It's not a contradiction at all. I know
the
you
K
think
value
it
is
is, but
reciprocal of the radius of the Earth, right? Yes or no?
it can be equated to that, yes.
Okay, what is it if you don't equate it to that?
It can be defined as, for example, 503 times the pressure over temperature squared, parentheses, 0.03
Yeah, what does that mean?
plus delta T.
Yeah, but what does that mean without a radius? But what does that mean without a radius? Yeah,
It is a measure of how much. It is a measure of how much a ray curves.
Oh, and curves. How do they? What is the value it's used to denote the curve?
You don't need to assume any particular value.
The radius of a ray.
For example, you can assume
the radius of a ray.
For example,
the radius of a ray, Charlie.
You can assume a flat Earth. Oh God, Indio.
No, dude, you know I'm right. Dude, you're cooking yourself, dude.
Do you agree that you can assume a flat Earth and still have a useful value for the for this K?
Yeah, but you're using the radius of a ray.
Of it?
Yeah, but it's still a radius of a ray, right?
Yes.
Okay. And then the K comes out of when you compare the radius of that ray to the Earth ray. You take this.
No, in this example, no, it comes out of multiplying 503 times pressure and some specific units divided by temperature square in Kelvin times 0.0343 plus dt over dz.
Yeah, that's fine. But
it feels like you accept this equation, right? I don't know if Mick has.
Yeah, that's fine, but it gives you the radius of a ray, and it assumes a spherically symmetric path of light.
Mick, do you agree with
Indio? Yes, it assumes a spherically symmetrical path of light which don't exist.
Mick, do you agree with Indio?
Dude, I'm going to have to be non-responsive. Are you going to keep being non-responsive?
Mick, do you agree with Indio?
Continue with Indio, dude. I'm reading. I don't know enough about this to actually agree or not. The hell are you asking me for? I've never seen this before.
Because you're the one who asked the original question, right? Of what are the necessary conditions for atmospheric conditions for you to observe an atmospheric refraction coefficient of near 1.
Great. So this supposedly would model that. And then the second question is, does it apply to what we were looking at?
Excellent. So the question has been reduced to, is there a value of P and a value of T and a value of delta T over Z, right? That would produce a refraction coefficient near 1. Are you happy with that reduction?
That's not the question.
Oh, God. Jesus Christ.
It's not the question, though.
I know it's not the question. I'm working towards it. After that question is answered, right? Because if he answers yes, right? The question has been reduced to that. Then we can go and see, okay, where has there been in the atmosphere a temperature of T with a pressure of P with a change in temperature over altitude of a specific value, right? Right?
Yeah, cool. But this assumes a spherically
Okay, excellent. You do agree.
Atmosphere.
Mick, do you agree?
It just assumes a spherically symmetric atmosphere.
Mick, do you agree?
This assumes a spherically symmetric atmosphere.
Excellent. All right. So now we just need to look for the particular values of P.
I know you don't want to acknowledge it.
T over Z, right?
Okay, I'm muting you. Okay, that's it.
Charlie,
you're going to address this. You're going to address this, Charlie. There's no way out. Okay, you can jerk off about your equations and explanations. Okay, this equation assumes a spherically symmetric atmosphere. You don't have that. Nobody thinks they have that. Doesn't model anything. That's why we asked you, do the meteorological conditions exist where you could get the appropriate value? And you pointed to an equation that doesn't imitate nature. And said, hey, I can manipulate the equation to give you some equivalent result. So if it predicts that, hey, something will be lifted up 10 feet, I can give you a spherically symmetric atmosphere model that'll say that it's picked up 10 feet. But so what? That doesn't model anything in nature. So address the lack that this equation models a spherically symmetric atmosphere. You understand? Oh, he deafened? No, Charlie's out of here. Bitch move.
Yeah, that guy's a piece of work.
Yeah, like, imagine struggling so hard not to present evidence. Dude, that was like an hour.
Yeah, it's crazy. Even if we had this model and we tried to plug in some values that applied to the black swan, we're still missing that. And that's the second part of my question to him, which, if we let this continue, he's probably going to skate around that, never producing any numbers that we can actually plug into these models. So, complete waste of time. Sorry.
Hey, I tend to believe the physics papers that I never read.
Last Lasu has put in the chat there, globe because information I can't disclose. Yeah, I heard his whole routine. Like, I don't know when that was. Then he tried to come in here and do that with me. Like, I've got top secret information that if I could show you would totally prove the globe. Like, oh my gosh, guy.
Well, that's not as absurd as the guy that came out from Ladies Night that said he can see that the stars are giant balls of fucking plasma millions of miles away.
Yeah. And you can see that they're helium. Yeah.
Yeah, that was pretty funny too.
Yeah, that's a Golden Globey for sure.
Now, Indio, I'm actually looking into this paper thing here, and I see, what you were talking about, the ratio between the radii, that's in section 2.1, right? You got that. But then looking down...
That paper is, listen, you should read that paper, because it goes over it in like the beginning of the paper, goes over the so-called terrestrial refraction, quote-unquote model, whatever you want to call it, in pretty good detail, like historical review, different experiments people did, different values they came up with, right? In the variation in values. So, like, you'll see some crazy variations in values of, like, different, like, they'll cite the paper, right? And they'll say, well, this guy measured over grassland and got these values. This guy measured over ice and got these values. But they're using this K coefficient value. But that's just matching, right? So, like, it's just matching it to the model, right? So you look through the theodolite, the little freaking crosshair you think you're supposed to be, or the little marking you think you're supposed to be zoomed in on is moved down, like, 3 inches or something. So you punch it into the model, like, okay, what is, like, assuming this model is correct, what would the radius of the ray have to be to move that, me citing that in 3 inches down. And they'll say, okay, well, the refractive index was a K equivalent to, 20 or something, whatever it is. So it's not even testing the model, really. It's doing observations and retroactively fitting the model to the observation. That makes sense.
I was just trying to find where this K equals R, like capital R over R, ties into the point number 2, what Charlie was going into, the X equals 503, et cetera, et cetera.
Didn't you say you pulled that out of one of the citations?
Yeah, so he was trying to dig into the second one, the X equals 503, et cetera, et cetera. But right above it, that's where the ratio between the radii comes in. And I think he was trying to point out that these are two distinct things. Right? Because, like, the K is not brought into that equation anywhere. Neither are either of the R's. So, like you were saying, this thing kind of goes into, like, a historical breakdown of different things. I think that's what I'm seeing here in 2.1. It's like they're saying, oh, at this point in time, these guys did this, and they came up with this model. And then later on, these other guys did this other thing. They came up with this other model as distinct from this first one. I could be wrong, but I'm just trying to reconcile that. I'm not sure.
Yeah, it says this K equals R divided by R, right? This definition is based on a circular arc used to model the often irregularly curved path of light. They're even admitting that it's not. That it's just a...
Exactly. And then below that, right, 2 paragraphs below, that's where the equation that Charlie was trying to expound upon comes in. That doesn't use the K equals R over R.
Yeah, the key of a particular point in literature commonly referred to as local record, denoted with X, is connected to the vertical temperature. That just, from what this says, tells you the refraction coefficient at a particular point.
Yeah. Yeah, exactly.
So in the vertical temperature gradient, so it'll tell you a point in the gradient from wherever the origin of coordinates, say ground level is where you start, right? So based upon this formula, if you plug this formula in, you want to know the temperature, say 5,000 meters. The X will be the refraction coefficient at like 5,000 meters, right? If you punch it in. Yeah. Because the delta Z is the what do you call it? Is the altitude, I think, right? Yeah, K per meter. Yeah. So X is connected to the vertical temperature gradient. Delta T divided by delta Z. That's K per meter. So that's temperature per meter. Yeah, that's in the parentheses, right? So that's going to tell you so this will calculate, if you want to know any point, you could figure out at any altitude what the refraction coefficient is if you have known pressure and temperature values.
Exactly. So that's what Charlie was trying to dig into, right? And saying there's no R in that. I mean, granted, Charlie did a poor job in presenting it. It was, confrontational shit. I mean, of course, it got heated and stuff. But I think later on towards the end, he was trying to emphasize that there is no R in this particular equation. That was the point. He kept asking for, like,
Can I hop in here for a quick? Hey, what's up, Mick? How you doing, buddy? What's up, Indio? How you doing, buddy? I just posted a video in the side chat. This video is of me on Lake Ontario, on the west side of Lake Ontario. Wicked conditions, wicked conditions, right? And I'm in Toronto, right? Obviously, I'm not in Mississauga. I'm literally in Toronto, and I'm panning the camera from my right to my left, right? And the reason why I'm doing it is I'm emphasizing that you're going to be seeing the lights, right close to me, and the distance is going to vary as I start panning the camera because it's literally the bend of the lake, right? So this is like a 30-mile bend, right?
That's 30 miles away.
Well, yeah, at some point it gets even further depending on which lights you're looking at, because that whole span of lights, they're all different, what do you call it, distances.
Yeah, so the part where you zoom in, there's a little
that's like that's the furthest, that's like right straight across. That's like from north to south.
Okay. Which lake is this again?
Lake Ontario, friends.
Lake Ontario, okay.
Yeah, if you Google it, you'll see the size of the lake, right? And then you'll see what I'm talking about.
And how high are you off the ground? 6 feet or something?
A little bit higher probably because I'm on some rocks or some shit, but yeah.
Okay.
But you can see how high I am off the ground, kind of, sort of like, yeah.
Oh, yeah.
I try to...
Let's say less than 10 feet.
Because before I zoom in, like, I think I show you what I'm standing on, kind of, sort of.
Yeah. There's about, like, let's say 3-4 feet of rocks and then you standing. So let's say less than 10.
And here's another crazy part. There's, like, a wave breakers. Like, they built these wave breakers, or I don't know where they built these things, right? And see how they're, like, below the horizon?
So you're looking right above them there? Right over them?
No, but yeah, it just emphasizes the perspective, right? How, like, it's how
like distance markers, let's say.
Right. Yeah, it's just a crazy nice observation, especially because it is the bend of the lake, right? So
that's pretty cool, man.
You're getting all of it.
Do you know how high the lights are on the other end? Like they're just homes or something, or?
Yeah. So they're not. They're like fucking. What do you call it? St. Catharines is the biggest city. It's like fucking townhouses.
Oh yeah.
Houses max. Yeah, the lights. You're just seeing street lamps. Those are street lamps, man.
Oh shit. Okay. So they should technically be a couple dozen.
Well, 600 feet of curvature missing at the across. You know.
600 feet. Okay. Wow.
Over 600 feet. Yeah. Well, supposed to be. Yeah. Okay. But the emphasis is if there was a curve at any point, right? If you were looking at these lights, at some point they'd start like dipping away from you downwards, right? But they don't. That's the whole point of this video. It's a flat horizon across, and it's a bend, right, where it should be fucking curving downwards, where the light should be disappearing at some point.
Yeah, I see that. Pretty good shot, man.
It's the S22. I actually I have this in Ultra HD, but Discord lets me only do 100 megs, so I had to convert it down to just HD.
Oh, okay. That's good. It's pretty clear what's going on there.
What kind of like the reason why I bring this up is because you guys are talking about lights and distances, you know, and bending over distances, and I'm here. I'm like, yo, look at this video. It gives you like from like 1 kilometer away to like fucking 50 kilometers away, and you literally get the whole span of it. And guess what? All the light is directly going into your motherfucking eye. There is no bending.
Well, that's what we were talking with Charly before, who was arguing the black swan thing, right? He was saying that basically, because I posted up a couple snapshots of the black swan values, like the height and the distance and shit like that, into the Walter Bisland calculator there. And in order to actually get, I'll post it actually again if you didn't see it there. In order to actually get the view that we get, there would have to be a refraction index of almost 1, which they qualify as being extreme. So I was going in with Charly as to like, well, under what conditions is this actually feasible? And then the argument started like, oh, well, it's technically possible. Look at my model. And then it just got hairy because like, well, where's the real world sample data fitted to this model, or under what conditions actually create this that we can actually find in any sort of given area, let alone the black swan? And I never really concluded, because Charly, is a bit of a dick. So anyway, I just posted it at 37.
Hey, Mick. Since
Well,
we have
that's
a little
good.
quiet time. Did you get to listen to my track? I think I sent it to you.
Not your
My
latest,
song.
not your latest one. Not your latest one.
No, man,
Not yet.
man.
I heard you. I heard you pump it the other day, though. Kind of
I
curious.
didn't pump it. Well, I mean,
Yeah,
somebody.
You spoke to somebody about it. You're like, oh, I heard that. I'm like, oh, fuck.
Yeah, it's. I mean, if you like deep house, it's all right.
Okay.
It's Indiemski.
I'll give it a listen.
I mean, the whole way through, please don't just fucking like, because I put a lot of work in the transitions and like it's progressive. Like it builds up and it drops. Trust me, it's fucking. Right. At some point, it's gonna be so crazy that I had to listen to my track a million times. I actually listened to it so many times. I'm like, the more I listen to it, the better it gets. I'm like, holy fuck, this is so good. But anyways, yeah. But that's because that's the kind of music I'm okay with. I listen to EDM all my life, right? So I can listen to fucking electronic music any day. Yeah.
I get that. That's pretty cool. I'm working on a couple recordings myself there, classical piano. And you have to listen to the thing like 1,000 times because you're tweaking little knobs and shit like that. To get it perfect. It's hard.
Yeah, and easy.
I'll check it out.
Oh yeah, thanks, guy. Hey, Flatter dude, what's up, guy? Holy shit, I didn't see you pop in.
I think he was here before you.
Oh, I see. I'm sneaking in.
You snuck in here, bro. So that's the one guy that I actually wanted to talk to because I know Flatter dude listened to my song, right? My bad. No, you're
getting good, man. Keep it up.
Shut the fuck up. Shut the fuck up. You didn't listen to that.
Shut the fuck up. Here, I'm gonna fucking play it for everyone right now.
No, don't play it here. No, that's not what I want. No fucking way. Bro, don't do that shit. That's crazy. You're crazy, bro.
Right. Let me go listen to it. Fucking mom.
Oh, so you didn't. See, that's what I'm saying. Shut the fuck up. You didn't listen. See, everybody's like, fuck this guy. I'm tired of his shitty music. Fuck this guy. I'm like, okay, guys, fuck it. It's all good. It's all good.
It's all good. Hey, music's music. I'm a big critic, so I'll let you know what I think.
Oh yeah, please, man. Don't be like nice. I need you to be fucking like hardcore, brutal fucking critic.
All right.